Well, hello again. We're going to learn two very important theorems and how to use them today. In a couple of days, we are getting ready to do some very important PreCal, and that is being able to factor any polynomial, no matter what it looks like. We've done a lot of factoring, but sometimes if the polynomial is too big and you're dealing with like an x to the fifth or an x to the sixth and it's really, really long, you probably wouldn't know where to start. So that's why we're learning this. These are two very important theorems. They're a little wordy and they're sort of hard to understand, but once you practice them, they're really, really easy. So the first one is, we're going to look at, let me go ahead and get back to the first page here. We'll look at the remainder theorem first. The remainder theorem says if you divide a polynomial by x minus c, then the remainder is f of c. So what does that mean, the remainder is f of c? What is f of c? F of c is fancy notation for the y coordinate at c. The point c comma f of c is a point on the graph of f of x. So this is saying if you do synthetic division and you go through that little process, which most of you have seen before, plus it's not very difficult, this is one way of getting a y coordinate on the graph. So the remainder is the y coordinate. Now why is that important? Well, if this remainder happens to be 0, then if r equals 0, that means that f of c is equal to 0, and that means that you have found a root, which also means you've found a factor, but that's what the factor theorem says. If you have found a root on the graph, you have found a place where the graph crosses the x-axis. And these places are very important. We did this with wiggles and crosses and tangents. So this is a process of finding where those are if for some reason you don't know how to factor it. So this is an important connection. If you do synthetic division and you get a 0 as a remainder, that number that you put in the box is going to be one of your roots. We're going to see that in a second. All right, now the factor theorem says that if you do have a root, then you have found a factor of the polynomial. And that's going to be very important because we're going to try and factor polynomials all the way down into their prime factors. And it's going to look something similar to a factor tree. If I had a number like 48 and I'm trying to break it all the way down to its primes, the very first thing I have to do is find any number that will go into 48 with a remainder of 0. You could start with 8 and 6, you could start with 12 and 4, 24 and 2, and then you keep going with that, and you keep breaking it down until you get down to prime factors. That's what we're going to be doing with polynomials. We're going to be breaking them down until we get to prime factors so we can graph it. And sometimes we just don't know where to start. This tells us where to start. If we can find out any time that the remainder was 0, so we have f of c equals 0, then we have found a factor, which is going to be a lot of synthetic division. But anyway, so that's what the factor theorem says. So let's go look at a specific example, and we're going to use the remainder theorem just to look at a y coordinate. Now, the remainder theorem says that if you divide by x minus 3, then the remainder is going to be the function value. Now, if you were to do this on an SAT question, you would actually plug in 3 for f. This is like the old method, or the old way. You would plug in 3 into x, and so you would do the following. 6 times 3 cubed minus 5 times 3 squared plus 4 times 3 minus 17. That's how you would do it, just by plugging in 3 for x. And you would get 6 times 27 minus 5 times 9 plus 12 minus 17, and then you would get 162 minus 45 minus 5, blah, 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 and you get 112. That's the old way. Now, we're going to use the remainder theorem to make this connection. And by the way, this means you have the point 3 comma 112 on the graph. So if you were to look at x equals 3, the y coordinate would be way up there. Okay, so let's use the remainder theorem to do this. Let's make this connection. The remainder theorem says if you set up synthetic division and you put the number in the little box and you do your coefficients going all the way across, making sure they're going in descending order, Then we drop our 6 down, multiply, add, multiply, add, multiply, add. The remainders theorem says the remainder is the function value. And looky there, we got the exact same thing, and this is not as messy as that. So this is a really nice connection for us. Now, for the most part, we're going to be wanting to get a remainder of 0 so that we know that we have a factor. But at least for now, this tells us the y-coordinate. So it's an easier way of finding y-coordinates. All right, let's do another example here. Use the remainder theorem to find the value of f of negative 5. So we're going to do synthetic division here, put negative 5 in the box. Now this is not going in descending order. It goes to the 4th, to the 3rd. I'm missing the squared term, and I'm missing my constant term. So I'm going to do 3 for the x to the 4th, a 2 for the coefficient on x cubed. There's a 0 coefficient of x squared. There's a 4 on the x, and there's a 0 at the end for the constant term. All right, so let's set this up. Multiply, add. Multiply, add. Goodness, what's 5 times 65? That's 325 negative. Multiply, add. And what is that? 1605. I think I did that right. 300 times 5 is 1500. 20 times 5 is 161. Yeah, okay, I think I did that right. And we add it up, and we get that the remainder is 1605. So that means that that's the y-coordinate. So f of negative 5 is 1605. That's way up there. All right, so that's what the remainder theorem says. It's an easier way for finding the y-coordinate. So let's go to our last example here for the real reason we're learning this. Use synthetic division to see if we have found a factor, a solution, a root. And this is a big, long polynomial here. Now, if this is a solution, this means that I'm going to get negative 4 comma 0. I'm going to find a root there. Now, one way to do this is plug in negative 4 and go through there and see if you actually get 0. Or we could set up our synthetic division. Now, does this go in descending order? 6, 5, 4, 3, 2, 1. Yes, we're good. So put our coefficients. 1, 5, 5, 5, 2, negative 10, negative 8. All right, let's see if we can do this. Drop our 1 down, multiply, add. Multiply, add. Multiply, add. Multiply, add. Multiply, add. Multiply, add. Boom. We got a remainder of 0. That means that this is a root or a solution of that graph. This means that we have found a factor, which means we can start breaking this down. We know this graph touches the x-axis at negative 4. But we also know the following. We know that x to the 6th plus 5x to the 5th plus 5x to the 4th plus 5x cubed plus 2x squared minus 10x minus 8 can be broken down into x plus 4. If negative 4 is a root, then x plus 4 is a factor. And what's the remainder? Well, all of this stuff right here. We divided an x to the 6th, so I'm going to get a 1x to the 5th plus an x to the 4th plus an x cubed plus an x squared minus 2x minus 2. The remainder is 0. So what I've done is I'm starting to break down this polynomial into smaller pieces. And then since I've found one root, I could even go to this next polynomial and try and break it down some more, to where if I got all the way down with nothing but linear factors, then I would be able to graph it, and I could put the little dots on the x-axis. I could look at my end behavior, and I would be like, hey, I'm beasting pre-calculus, and I'm doing it all in my head, which is where I need all of you to get. Because remember, we're in pre-AP pre-calculus, so we need to learn this. Okay, so I will see you guys tomorrow.